Now we introduce Thomas Elliott, who Ian has already sort of mentioned really nicely. He is the director of the CrowtherLab, which is based in Zurich. And the CrowtherLab is an interdisciplinary research team using ecological science and machine learning to inspire the environmental restoration around the world. And yes, I welcome you to the floor, Thomas. Thank you for coming.
Cool. Thank you very much for that introduction, Samantha, and thank you to you and Lauren and Angela as well for putting on this conference at such short notice. It really is quite dynamic and a great example of how we can switch online very quickly. I'd also say thanks to Ian as well for the very kind words and the introduction about the lab. Unfortunately, Professor Crowther hasn't been able to join today, but I'm going to be stepping in his place and trying to give you a bit of a sense of the science. To give you a bit of context, I'm not actually a scientist myself. I am sort of operational at the lab and manage kind of the partnerships with Jay that Ian was talking about and the other partners that we have. But hopefully I can give you a sense of the scientific journey that we're on. And I thought I'd start off, first of all, by just playing a bit of a video which provides an overview of the research we do at the lab. I should also say Angela's tried to encourage me to make this as interactive as possible. So as we go through, I've kind of got some multiple choice questions. I've realized looking at this talk, that it's just a series of revealing information that we've discovered through the course of our research. So I've tried to make it a bit more interactive. As those come up, I'm really interested to see your feedback on that as well. So we'll start up with the video.
Humans have always learned to overcome problems with the help of a simple process: trial and error. But unless this information learned is retained, trial and error will always reach a dead end. Networks are what enable us to process and disseminate this information. Several million years ago, our ancestors were experimenting with their own versions of trial and error. Whether this involved the food they ate or tools they used, it was the network of neurons in their brains that allowed them to learn from their endeavors and ultimately continue to evolve. Over many generations, as our communication skills improved, we grew another kind of network, facilitated learning at the community level, social level. Fueled by our capacity to communicate, suddenly, if one person learned something, the whole group would share that information. Now we started to develop on a new timescale. Within just a few thousand years of community-level problem solving, human population growth began to explode. Unfortunately, a rapid expansion spread a whole new generation of problems. A series of global issues threatening all of society. The scary truth: we no longer have millions of years to adapt. We have only decades. So, is it possible for humankind to overcome these global scale problems in a matter of years? We believe it is. And by drawing on the same principles we always used. We use machine learning to perform rapid trial and error calculations. It's billions of times faster than human learning. And to process this information, we work with a vast network of thousands of ecologists from around the world. By allowing us to detect global patterns from local observations, these networks help us to understand Earth's capacity to store carbon. With these basic principles, we hope to generate rapid ecological understanding and inspire a global restoration movement to address the threat of biodiversity loss and climate change.
Even more of us now recognise the threat that climate change poses both to us and to future generations, particularly in light of the incredible 12 months we've had in terms of natural events all around the world causing various types of disturbance, from the forest fires and flooding all throughout Australia and the 11 million hectares that have burned most recently. And we're now seeing you know, the message that came from scientists that Ian referred to earlier in his report 2 years ago as part of the IPCC report on 1.5 degrees come true. In order to hold the global increase in average annual temperature to 1.5 degrees, you know, we need to cut carbon emissions by half, from 40 gigatons that's currently at per year to 20 gigatons every year. And the reality is, I'm sure as many of you guys are aware, that it's not that simple, cutting carbon emissions. In order to do that, you know, climate change is an incredibly complex topic and it's not easy. But our research at the CrowtherLab aims to try and simplify this topic to generate a more holistic and spatial perspective on the climate crisis, to try and guide more effective and targeted strategies to address it. Because the thing we're dealing with, the atmosphere, is actually incredibly thin. It's analogous to the width of the rubber on a balloon. And every year, we're emitting 10 gigatons of carbon into that space. So to kick off the interactive section of the talk, I think this is our first question. Angela, I don't know if you're able to trigger it, but I just wanted you guys to get a sense of how much carbon we're emitting into the atmosphere each year. How much does that 10 gigatons equate to in terms of the weight of Empire State Buildings? Is it A, 10,000, 17,000, 27,000, or 37,000 Empire State Buildings? 27,000, wow, I'm impressed. Everyone's knowledge of carbon, yeah, that's exactly right. We've got 27,000 Empire State Buildings. It's the equivalent that we're emitting into the atmosphere every year. And of that 27,000 Empire State Buildings, approximately a third of that carbon gets absorbed by the ocean, a third of that carbon gets absorbed by the land, but the remainder stays in the atmosphere. And over time, sorry, I've lost the ability to move my slides. Over time, that carbon is accumulating into the atmosphere and causing this problem. And since the Industrial Revolution, we've built up about 300 gigatons of carbon into the atmosphere. And the message from scientists from the IPCC report is that we have to stop increasing the size of that problem. That has to be our highest priority, cutting emissions going forward. But we also have to think about technologies and solutions for drawing that carbon down from the atmosphere. And we at the CrowtherLab consider that there is actually a greater threat that underpins climate change, and that's the loss of biodiversity. When we lose natural ecosystems, additional carbon is actually emitted into the atmosphere. But much, much more importantly than that, these ecosystems are the Earth's regulatory system. They are the lungs that draw down carbon from the atmosphere and they store it within vegetation and soils. And I just thought I've included here a NASA simulation of that system. It's carbon dioxide movement throughout the year. And you can see the high concentrations of carbon indicated by red colors in the high latitude regions. But as we move through time and tick into late spring and then summer, we kind of see these concentrations start to fade. And that's driven by one thing. It's the emergence of leaves on trees. This very simple ecological process has a huge impact on the carbon cycle every year. It's one of several massive ecological processes that are taking place, and they all balance one another out. The problem is, as you can see in the heavily industrialized parts of the world, is that we continue to emit this 10 gigatons of carbon each year, and it's not offset by any uptake. So we're gradually building up that atmospheric burden and we're warming the climate. But given the massive scale of these systems, given the huge impact that they can have, we consider that they should be up there amongst the top climate change solutions, ecosystem restoration. But the problem is, up until now, we've not really had a great understanding of the power of these ecosystems. We've not been able to quantify those ecosystems because they're so variable in different parts of the planet. Now, in 2014, 2015, we were approached by a youth NGO called Plant for the Planet, which has 70,000 child ambassadors all around the world. And they came to us with a relatively simple question, which was, how many trees are there on the planet? And the truth was, we didn't really know. And that's because our understanding of these global ecosystems is limited to top-down satellite information. But using that information, NASA had been able to estimate that there were approximately 400 billion trees on the planet. And up until 2000, 2015, that was the number guiding the UN's billion tree campaign to plant 1 billion trees. But in our lab, we knew that really getting a handle on this number required something more. It required sort of an army of scientists going out into their local regions, collecting physical information about the number of trees, the size of those trees, and the species, recording the species type of each of those trees, and then taking that information and using the latest developments in machine learning and artificial intelligence, we've been able to correlate that information with things like climate characteristics, topographic information, and soil characteristics to get a much better understanding of the spatial distribution of the global forest system and the tree density. So this is the map that we produced as a result of that paper in 2015 to map the planet's trees. So I guess my second question is, how many trees do we estimate there are on planet Earth? Is it A, 300 billion, B, 800 billion, C, 3 trillion, or D, 6 trillion? Oh, 800 and 3 trillion came in neck and neck. So the answer is actually 3 trillion. The study found that we had 6 trillion trees before the onset of human agriculture. But at the moment, we've sort of decimated 50% of those trees to make way for urban areas and agricultural areas. And because we have information about the species types and the size of those trees, we're also able to make an estimate of the amount of carbon those trees store. So again, another quick poll question: how much carbon do we think is stored in those ecosystems, in trees around the world? Do we think it's 300 billion tons of carbon stored in those trees? So the same amount that's currently sitting, the anthropogenic amount sitting in the atmosphere? Is it 600 gigatons, 900 gigatons, or 1,200 gigatons of carbon? Fantastic. So I'll reveal early. It's 600 gigatons of carbon.
Ooh.
So, and again, that's 3 out of 3 pretty much. So very informed audience. But yeah, that is, so it really puts it into perspective. Again, when we're thinking about that 300 gigatons in the atmosphere, how much carbon we've stored within the trees. So it's partly a risk because we're losing so much forest each year, but it also shows the potential of this ecosystem to store carbon. The great thing about, so the next question that kind of came through from various NGOs like Plant for the Planet was around target setting. So the next question that they had was, what is the potential to store trees on the planet? And we discovered by sort of training these models that we have on the pristine ecosystems that have very little human disturbance in them, these unprotected areas, we're able to make even better predictions about the potential to restore forests in the absence of humans. And so we were able to find or identify the areas on the planet that if we were to sort of remove humans from the planet, how would these forests regrow? And obviously it showed this map here that there is vastly more room on the planet for trees in the absence of humans. But obviously we do exist, we are here. And so in order to identify that actual tree restoration potential, we have removed existing forests, existing areas used by humans for agriculture, and existing urban areas to identify the actual restoration potential for trees around the world. And so the fourth question we have here is, how much of the Earth's surface is available for continuous tree cover if we remove agriculture and urban areas? This was a huge paper that we had in July last year, which had a global audience reach of 160 million and really went viral. So hopefully you guys have a sense of what the reach of this paper.
Let's see if we can get the score record. We can maintain our track record.
700 million. It's actually 900 million. So it's the first one you got wrong, incredibly.
Oh!
The biggest finding that we had. Yeah, it's actually 0.9 billion hectares around the world that's available of continuous tree cover that is available for tree restoration. And we're estimating that that area could store an additional 1 trillion trees. And it's obviously had huge pickup and huge reaction from governments around the world. We've seen Canada, Australia, the UK in the general election last year was talking about tree restoration, and even Trump and the USA have now chipped in with tree planting targets with the 1T.org initiative launched at the World Economic Forum earlier this year. And we're estimating that if those trillion trees are restored to maturity, it could actually store in the range of 100 to 200 gigatons of carbon. Whilst there is huge uncertainty in that estimate, and it could take a century to accumulate, I think there's no denying that this is, the first quantitative understanding that we've had of the potential to restore trees on the planet, and it has to be considered among all of the other climate change solutions that are out there in terms of combating the threat of both biodiversity loss and climate change. So moving on, the next sort of suite of models that we're thinking about building is really, I guess, some of the scientists in our lab would call it the holy grail in ecosystem science, is trying to understand the billions of species that exist beneath our feet, the soil organisms. This is by far the most complex and diverse community in the terrestrial biosphere. And we believe that really getting an understanding of these below ground systems could be the key to unlocking the true potential of nature-based solutions to climate change. And using sort of the same techniques that we had using for the trees, we've identified similar patterns in the distribution of soils around the world, and soil carbon in particular. So we had a data set here, not quite as big, not the 1.2 million forest plots, but we've taken 60,000 forest plots around the world and measured the carbon. And I think this is another question I have. So how much soil is estimated to be stored in the Earth's soils? Again, to give you guys a bit of a sense, 600 gigatons, 900 gigatons, 1,200 or 1,500 gigatons. 1,200, that's actually, so the second one we got wrong, but it's the 1,500 gigatons in terms of soil carbon. So it's a huge carbon store, and it's got absolutely massive potential. And I just wanted to explain that, or to show that in a slightly different form with this graphic we have. So you can see everything on the left-hand side of this graphic above 0 degrees. 0 on the left-hand side is the above ground carbon stock. So that's the carbon that we've got stored in the Earth's vegetation. And as you might expect, if you're standing at 0 degrees latitude in the middle of a tropical rainforest, you'd be surrounded by the vast majority of the Earth's vegetative carbon stocks. But what a lot of people don't realize is that if you take the time to look sort of in the top 10 to 15 centimeters of soil, you actually have 5 to 10 times more carbon stored below your feet. And what's even more surprising to some still is that if you travel 50 degrees north in latitude to the boreal regions of North America and Northern Europe, we can have sometimes 10 to 15 times more carbon stored in the soil beneath your feet. So it's really giving us quite an important perspective when we're looking at ecosystems. If you want to plant trees, undoubtedly the tropics is the place to focus. But if you want to preserve soil carbon, these boreal regions where we've got really cold temperatures that are really slowing down organic decomposition are going to be really important for the preservation and accumulation of soil carbon. And finally, we're also able to use similar techniques with our colleague John Sanderman to look at the potential to store soil carbon going forward if we use better soil management practices. And it's showing that restoration potential is in excess of 116 gigatons of soil carbon. And the great thing about the soil carbon is that it's not limited to one particular ecosystem. It's not limited to forests. Of course, forests play a really important role, and we can store approximately 30% of that potential in the soil beneath the world's forests. But we also can store that soil carbon in grasslands and shrublands. So although grasslands and shrublands have a relatively shallow amount of soil carbon, they're spread over a huge extent of the planet, and so can store 39% of that 116 gigatons of carbon. So it's a really important ecosystem. And the great thing about the grasslands and shrublands is that it doesn't necessarily come at the expense of other land use types like agriculture. You can still have agriculture and very high soil carbon storage in order to promote productivity. And finally, we look at the wetlands and the peatlands, which is an incredibly powerful ecosystem for storing carbon. These wetlands and peatlands take up only 5% or less than 5% of the Earth's surface, but they store an incredible 31%, almost the same as forests in terms of that soil carbon storage. So bringing it back into context, this is all showing that the natural system, these natural ecosystems, have an incredibly powerful role to play when we're talking about pulling down the 300 gigatons of carbon in the atmosphere. But like any solution this powerful, it also comes with very high risks. And what we're seeing, what we're hearing anecdotally, is that in tropical regions around the world, we're seeing only 30% of the trees planted actually make it to maturity. And that's because we're either planting the wrong species or we're planting these trees in soils that can't support them. And when they fall and die, they're actually destroying natural levels of biodiversity. So doing this without being informed can be ineffective, or sometimes it can actually even be damaging. And with this huge swell in ecosystem restoration, it's a real concern, and it's something that the restoration movement is now trying to tackle, trying to move away the narrative from tree planting to something more akin to tree growing, or even better still, forest growing. And the really exciting thing, as Ian alluded to earlier, is that we're now partnering with Bula and some interns on the Unitech program to try and think about how we can solve some of these challenges that restoration projects are facing around the world. So we're connecting with hundreds and hundreds of restoration projects that have contacted us since that paper came out on the tree restoration potential. And we're now trying to provide them and create new maps to tell them, you know, how many species to plant in a particular area, what particular species they need to plant in order to promote either biodiversity or carbon storage. We're giving insights into the microbial and the fungal community in order to maximize carbon storage. And we're also now developing a model which is going to tell us the impact of planting forests in different parts of the world on the temperature. Because what a lot of people don't realize is that whilst forests generally do have a cooling impact on the climate by drawing down carbon from the atmosphere, in some regions, dark colored forests can actually absorb the sun's energy and warm the climate around them. So it's really important to get an understanding of the impacts that you're having. And finally, probably more important than the ecological context is the socio-economic context. Because ecosystems are intrinsically linked to the people that live there. And in the past, we've seen too many restoration organizations move into an area, buy up land, plant trees, and exclude the local communities. And not only is that socially irresponsible, but it's unsustainable, because those communities are inevitably going to cut down that forest for their own livelihoods, as we would. And so we really want to make sure that doing restoration in combination with local communities is the highest priority. We need to make sure that funding goes towards those communities, they benefit from the ecosystem services and the improved agricultural productivity that comes with it. And finally, just to summarize, you know, given all the attention that we've had, and this is something that we're developing with the Unitech interns, the priorities in terms of doing restoration in the right way, setting some restoration principles. We're talking about reducing emissions has to be the highest priority, as you've probably got from the sense of my talk. There isn't enough room on the planet for us all to plant trees and offset our carbon emissions. It absolutely has to be done in combination with reducing emissions. Restoration has to be ecologically informed. Planting trees in the wrong, unsuitable ecosystems can actually have negative consequences. I've highlighted. It needs to be done in a socially responsible way, as I've touched on. And of course, we need to, probably, this has been touched on less in the media than anything else, but we have to protect old growth forests. These are really important stores of biodiversity and carbon, and they have to be a huge priority. You know, we'd be better by cutting down a hectare of old growth forest. You're going to have a much worse impact than growing a hectare of new forest. And so preserving these ecosystems has to be our highest priority. And then once we start restoring, we can tip the carbon balance in our favor. So finally, sorry, I know I'm short of time, so I'm now rushing a little bit. I'd like to leave you with a practical tool on our website, a call to action, and as Angela asked, a reflection exercise, sort of how to think about what that might be. So on the map section of our website, you can explore all of this information that we've been talking about, the climate characteristics, the soil, the nutrients, and the tree data. We've got it all on there, and that's really helpful to sort of think about how you can explore potential, set goals, and work with partners to do initial planning and assessments. And we're now going through a process of updating this tool so you can compare different layers, upload projects, and see the data for those particular projects. And obviously, we're creating a map of the 60,000 tree species that exist around the world so people can understand what species to plant in what particular regions. We really want this to be as beneficial as possible to restoration organizations everywhere. So if you have any feedback, if you have the chance to go in and think about the functionality, we'd be really grateful for your feedback on that. And then thinking more generally about the reflection assignment, one area that we're really interested in sort of growing this research is around agroforestry. We think it has huge potential to sort of engage local communities, but also have that economic impact that we were talking about. We've done research in the last year which shows that actually growing shade trees amongst cocoa plantations can actually increase yield as well as protect those plantations from climate change and disease. And so it's a win-win when we talk about also drawing down carbon from the atmosphere at the same time. So being able to do a global study on the potential to store carbon within agricultural systems, we think could really trigger even greater engagement on this. So I'll leave it there. Thank you very much for your time and for listening.
Thank you very much, Thomas, for this presentation. So I have to say we have a lot of questions in the chat, but most of them would actually feel a bit more like a test to you because they are quite technical and detailed. So what I will do is among those ask the one that had more upvotes. So Martin, if you could unmute yourself and ask the question you wrote in the chat.
Sure. My question was that some things like, for example, soil trapping in cold climates is prone to be triggered by global warming and releasing all the carbon again. So which would be the solution that is least endangered by global warming or most likely to survive and be a lasting solution?
So, the issue with, I'm not sure I understand the question. You're saying the soil is not a great area to focus on because of the warming impact and the fact that as the earth warms, we're releasing more and more soil carbon. Is that your question?
Yeah, exactly.
Yeah,
so
I think
trees, because they reduce the heating, would probably be the best solution according to what you said after I posted the question.
Yeah, I think for us, the priority is initially restoring forests in tropical regions. I think that's the easiest win that we can have. And yes, there is an element of heating that's coming in, and the high latitude regions that have stored lots of soil carbon and have slow composition at the moment, each year that decomposition is speeding up and we're actually losing soil carbon at an annual rate. And there's not a huge amount we can do on that. In the kind of temperate regions, you can treat soil by putting on biochar and looking at having sustainable cover crops in the off season to try and protect the soil carbon. But yeah, I think we see the easiest win as restoring forests in the tropical regions and trying to reduce the impacts of climate change through that.
Okay, thanks.
Okay, great. Then, yeah, there seems to be a lot of interest in these more detailed questions. So, Len, if you could ask your question around Central Africa.
Yeah, so Thomas, thanks for your great infographics. In the beginning, you showed us this video where you see throughout the seasons how CO2 changes. And then it seems like in the center of Africa, there was this red part. What exactly is there happening in Central Africa?
We haven't investigated. That's a NASA simulation that we've taken just to show the impacts of how carbon changes throughout the year. We haven't investigated the exact movement of everything on that screen, but I guess our assumption is that is the release of emissions from industry. So it happens there. I think you saw some in China and India, and I think we saw some in North America as well. I would have to go away and research exactly what those things are.
Okay.
I assume it's heavy industry that continues to release emissions outside of the regular cycle of. So each year, ecosystems will emit about 10 times more than the human emissions. Trees and vegetation release about 120 gigatons of carbon, and at the same time they're drawing down 120 gigatons of carbon when the leaves come out, and that's primarily what that cycle is showing, and everything else is down to human emissions that we're seeing, and that's outside of the main sort of red that comes up.
Okay, thanks.
Great. And then Jess had asked about, besides the emissions you showed us for the soil, what is happening in the rest of the planet. So Jess, if you can ask your question.
Thank you. Yeah, my question evolves around oceans. So we've now been looking at land-based solutions. Yeah. However, our oceans are way more vast, 70% of the Earth. So how much CO2 is stored in underwater vegetations, especially kelp? And then what's the potential there?
Unfortunately, we focus on terrestrial ecosystems, so we don't have data. Well, the data does exist, and I can go in and get that for you, but we're focusing on terrestrial ecosystems primarily. But as I said, the oceans are absorbing 30% of annual emissions. But what we're finding is that they're, as I'm sure you're aware, they're acidifying and taking in less and less carbon as we go. They're actually becoming a carbon source in some areas. But yeah, I can go in and find that data. Maybe we should add that in terms of, we've covered sort of 4 ecosystems on the terrestrial land, but oceans are probably a good one to add to this.
Thank you.
And then thank you. And a very timely question from David Kinsella around the impact of the current pandemic.
This is really interesting, Thomas. Thank you. Could you have an understanding of the impact, the total impact of the pandemic on 2020's carbon output?
I have no idea, unfortunately, what that impact is going to be. From what we've seen in the media, and obviously the fact that we're doing these conferences digitally, and the fact that Ian's talking about, you know, as being on lockdown for another year, you'd think the impact is going to be absolutely huge on that 10 gigatons of carbon. But it'll be really interesting to see how much that 10 gigatons come down. Does it come down by half? The IPCC report, and it'll really start to give us a sense of whether it's achievable. So I'll be really interested to see at the end of the year how it does play out. But yeah, again, we can go away and look into that and get back to you.
I'm sure you don't need any more projects. It would be really interesting to see what comes out of the watch.
Yeah, no, really good point.
Okay, good. And then to close with the technical questions and move to a question which is very in line with the symposium topic. Charlotte, if you could ask the question you wrote in the chat.
Yeah, great talk. Thank you so much, Thomas. I was wondering, just based on the topic of this entire symposium, how we as individuals can support your reforestation mission. Obviously, it's not feasible for us all to go out and start planting trees. You have some great advice on like which trees are best in which region. But how can we support you as individuals or as Unitech as a whole?
Yeah, so I'd say we have kind of 3 calls to action when the paper came out. And those were, the first one is absolutely, if you want to get involved and plant trees, please go onto the map, go onto our website and see what the potential is in your local area for planting trees. And we've tried to add species recommendations in the places that we can as much as possible. But as I say, we're working on doing a much higher resolution species distribution model from the 1.2 million forest plots that we've got. The second thing you can do is to donate to, there's thousands of restoration projects that are already out there. We've listed the top sort of 10 to 15 that we're working with on our website. These are organizations that we're now getting the sort of the Unitech interns to sort of help out with building that network, getting to know these restoration campaigns, thinking about ways that they can collect data. The strength of these models is in the data that we collect. We're the first group to sort of have this global data set of 1.2 million forest plots. It's got 30 million measurements of biodiversity around the world. And the more that we can improve that data, as you've probably seen from the map, it's primarily from the US and Europe. We need to start adding data from other countries. You know, Africa, China is a big hole in that data set. And once we start getting that information, we can provide much higher resolution models. And a lot of what the projects that we collaborate with are asking for is better information on monitoring. How can they monitor their forests and show to potential funders the success of their efforts? So the more data that we can get, the better. And that also links to the question, the sort of thought exercise that I had on how can we get data, yield data for agriculture, because we think that's got such huge potential. And the final area third area that we think you can help is by just supporting companies that are sustainable in what they're doing and having an outlook which is having a positive impact on their ecosystems, and making sure, you know, how you investing your money wisely, essentially supporting companies that have similar aspirations that Ian was talking about this morning.
Thank you so much, Thomas. From what I understood of your sort of what we should be discussing now, it was around how we can integrate the agroforestry in our local communities or in communities in general.
Yeah, I think overcoming the kind of data challenge that we have, and how can we as scientists, you know, industry has incredible potential to scale solutions. We as scientists are finding out new research avenues, but how can we help sort of scale ecosystem restoration and scale the collection of data in order to make our findings even more impactful?
Well, thank you so much for summarizing that. And then, yeah, hopefully we'll break out into groups now-ish.
So yeah, we'll break now and we'll have 8 full minutes, almost 10 minutes. So this will be a longer slot. Okay, let's see how that works. There we go.
Cool. Thank you very much.